this smart method is called Horner's rule. Yeah, so let's study this Horner's rule. All right. Oh, yeah. This one. Yeah. So a lot of things. All right. Yeah, good. Yeah. All right. So now we consider the general case. Yeah. All right. Yeah. So that's the old story. Yeah. So the experience we want to borrow here, the key factor factorization. So now we want to apply the factorization in which way? That's important. Apply the factorization in which way? Yeah. Strategy for generalization. What strategy? Do factorization as much as we can. I draw this underline, as much as we can. But because when you do factorization, you have many different ways to do it. Many different ways to do factorization. Yeah. All right. As much as we can. What do you really mean as much as we can? Yeah, we know its meaning, as much as we can. All right. But here, the question, how do we do it, right? Execution. Last time, after we have the strategy, we need to take care that execution part. As much as we can, this related to execution. Yeah. All right, so here there is an important idea here we call a greedy idea. Greedy idea. Greedy. Yeah. People try to get money as much as they can. That's the greedy, right? Yeah. Yeah. Sometimes, not always, right? Sometimes, yeah. Yeah, but here we borrow that kind of, real life situation, put it in the algorithm. We have an important algorithm we call the greedy algorithm. Greedy algorithm. Here, this is our first view of greedy algorithm. Yeah. We try to use some particular property as much as we can. That's the greedy strategy. Greedy strategy. Now here, let me show you how to do it. How to apply the greedy strategy here. All right. Now let us consider P3. Yeah. Increase the problem size a little more from 2 to 3. Yeah. All right. So let's do another round factorization. Yeah. As here, let me show you how do I interpret as much as we can. All right? Yeah. So when we apply the factorization, we should cover as many terms as possible. Yeah, that's one place, as much as we can. So we cover as many terms as possible when we do factorization. Yeah. What is the maximum number of terms they have the common factor, right? Yeah. Yeah. The whole polynomial, all the terms, if you look at all the terms, they do not have common factor, right? They do not have common factor, yeah. So you have to reduce the number of terms, but you don't want to miss anyone. You want to include the largest group that have common factor. That is the last 3 terms, right? Last 3 terms, they have common factor. Now, we do the factorization covering the last 3 terms. That's as much as we can, as much as possible. Okay? All right. Yeah, that's the greedy algorithm, greedy strategy. Yeah. For the remaining terms, do the same factorization. Yeah, this is the first time we do the factorization. Right? The first time we do the factorization. But inside the parenthesis, can we see some more terms? They still have common factor. Right? inside the parenthesis, our property, our common factor property is still there. We can still take advantage of it as much as we can. That means we need to get into it and do more factorization. That's the greedy strategy. Yeah, greedy strategy. All right. Yeah, that's simple, yeah, but that's the greedy strategy. So another round factorization. You can see we do 2 round factorization when we consider cubic polynomial. Degree 3 cubic polynomial. Yeah. All right. Now let us push to the general case. With these 2 examples, I think we have the experience getting to the general case. All right. Yeah. Oh, sorry. Yeah. Next. Now the general case. This is the Horner's rule. You can see we do factorization round by round. Every time we reduce the number of terms to factorize common factor x until we cannot do anything. Right? Yeah, that's the procedure. Question? Yeah, looks like, all right, yeah. Yeah, think about that. That's the Horner's rule. Yeah. That's the smart way. Smart way. Okay? You can see at least this way is quite different from the plug-in way, right? Plug-in way, completely different. So we expect the result, the outcome should be completely different. The outcome should be different, right? All right, so let us look at the outcome. Yeah. Let's do the counting. Now we need to count the number of multiplications we need for this polynomial evaluation. Counting by reference. Now you can see the method I explained last time is very useful here. Very useful here. Counting by reference. Otherwise, try by yourself. If you do the counting, you have many ... here. How do you keep track of the ... right? How do you keep track of it? ... Okay? So now you count the number of multiplications. Anyone can give me an answer? Answer? Answer, number of multiplications.
N multiplications.
N, yeah, this didn't give me N. So you agree? Look, all right. Anyone want to say N plus 1? Yeah, because that kind of thing, usually not easy to tell which one is correct. Yeah, answer is correct, M. Yeah, the answer is M. But here, for some students, if you feel hard to find the answer, here, let me show you this method again. Try to learn this counting by reference method. Yeah, all right, here. Multiplication, when we count multiplication, this is one multiplication, right? When we do the multiplication, we want to associate it with another mathematical object that is easy to keep track, right? Yeah, easy. So how about we associate this multiplication to subsquare A1? A1, 1's subsquare. How about that? All right? The second multiplication, this one, how about we associate with 2 subscript nearby? Reference, 1-to-1 correspondence. ... we don't worry. The last one associated with, not last one, last parenthesis. How about that? Last parenthesis, yeah. Because there is another multiplication here we associate with subscript N. How about that? Yeah. Now, when you count the total non-multiplications, That's the same as count the total number of subscripts from 1 through n, consecutive numbers, how easy it is, right? Think about, so this is a perfect example showing you why counting by reference is effective. One-to-one correspondence. If you can find that relationship, one-to-one correspondence. Yeah. All right, yeah. Okay, now the answer we need to do the comparison. Yeah, so here, yeah, all right. Okay, yeah. And next, we need to do the comparison with the old method. We use this many multiplication. Remember, old plug-in method. New method from 1/2 n times n plus 1 greatly reduced to n. How big it is? Can you imagine how big it is? You know, it's a big reduction. Big reduction, but how big it is? It may be hard to visualize it, right? How big it is? Hard to visualize it. Yeah. Here, we need to do some visualization step. We want to really find some concrete example to give us clear sense about the difference. Otherwise, you may not appreciate the big improvement. You may not appreciate it. Yeah. So we want to see that huge difference. All right. So here, we will do that part. Here, I show you, I want to use a simple example to let you see the big difference. Yeah. So what difference? Impact of the multiplication reduction. How huge it is, the impact. Yeah, this reduction. All right. So we want to do the visualization here using some concrete examples. Real world examples. First, let us try n equals 1,000 and compare these two numbers. When there are 1,000, n, degree equals 1,000. What is the difference between those two numbers? That's easy. We plug in n side only 1,000. That's quadratic. This is a quadratic polynomial. That side 500,000. Is the difference big? Reduce. You can think about if you are given a problem with degree 1,000. If you use the plug-in method, you need to use 500,000 multiplications. But if you use Horner's rule, you only need 1,000 multiplications. How big it is? The difference, improvement. 5,000 to 1 ratio. How big it is? 5,000 to 1. Yeah? All right. Using the old method, the time you need to wait for the response, 500 times of the response time of the new method. How about that? Yeah, question.
I have a question for the last slide, if you can go back.
All right. Yeah, I need to, all right, all the way back. All right, yeah, here.
Yeah, I was wondering, would each term have like, instead of one, actually have two multiplications? Like, you have x times a1 and then that times, I guess if you want to go to like, or if you look at the one above, the simpler formula, for the simpler case, like you have x, and then in parentheses you have two terms that it's multiplying with would it be like, instead of n, would it actually be like 2n or 2n minus 1?
1 here, 1 here, all right? The degree is 3, So 1, 2, 3. That's all we need. Don't worry about the plus sign. We ignore the addition. Yeah, because 10 to 1 ratio, remember? Addition only 1/10 of the multiplication. So we don't worry about addition. Yeah. Later you will see the addition number, no change. The same as the old way, no change. Nothing to lose, right? We do not lose anything in addition. Nothing to lose. So we keep the same amount of time for the addition part. No gain, no lose. That's nothing, right? Addition, nothing. So you ignore it. You can safely ignore addition, but only look at the multiplication. Yeah. All right, yeah, okay. Let's go to the, this point. All right, 500 to 1 ratio. That's the big difference. Waiting time. You can see, one guy, miserable, right, sitting there waiting 500 times of the other guy only, 1, right? How big it is, right? You can see. But the story goes on with even bigger impact. Yeah, this is our first example. Yeah, I want to show you the second example, 1 million. How about that? We change because here, right now, it is the big data time, right? Yeah, big data time. So the data size goes to 1 million. It's normal, right? People need to deal with 1 million data items. That's reasonable, right? So when under that situation, 1 million still, but look at how many zeros you have here, there, right? Yeah, right? Anyone can call that number. So how do you call that number, right? 500 billion, is that 500 billion, right? Yeah, because 90, that's billion, 500 billion, okay? 500 billion versus 1 million. What's the ratio? 500,000 to 1 ratio. How big it is, right? How big it is. But that's just number, right? Even I show you that huge number ratio, for many people, it's still hard to visualize how huge it is, right? How huge it is. Just a number, we do not have a sense. We do not have a clear sense about that number on paper. We know it's big, but we don't know how big it is. Let me use another way to show, you really have the good sense about it. All right, so what's that? How about let us add a time unit 1 second. This 1 means 1 second. 1 second. Yeah, you know how long is 1 second, okay? This 500,000 means 500,000 seconds. How about that? How long is 500,000 seconds this time? Converted to number of days. We can do the conversion, right? Number of days. All right, yeah. So that's the difference. Approximately equal 5.8 days. Do the calculation, divided by 60 to minutes, 60 to hours, 24 to days, then you will get this 5.8 days. Now, think about 2 solutions. Think about, here we make this story associated with real-world experience. 2 business solutions. Solution 1, plug-in method. Right? Evaluate polynomial using the plug-in method. Okay? Yeah. Solution 2, Horner's rule method. All right? Yeah. Yeah. Now, think about if you deliver 2 solutions to your customers. Yeah. Your customer paid the money. Yeah. You deliver these 2 solutions. Look at the difference. Okay? Do computation on a huge polynomial, right? The solution 1, after your user hit enter, they can take a vacation, right? 5.8 days, almost 1 week. Long, yeah. Then come back, check the answer. Solution number 2, after you hit enter 1 second, you see the answer. How big it is. Right? So from this example, you can see the impact, the big difference between a good algorithm, this is a good algorithm, and a bad algorithm. How about that? Yeah. Yeah. It's very common in the real world. You can make improvement as big as this one. As big as this one. Okay? So that's the goal, or one of the goals. We are here to learn the algorithms. We want to do a good job of this kind, not that one. Okay? We want to do as fast as that one. Okay? Now, our project number 1, programming project number 1, this topic. I formulate this problem in a way you do comparison. I give you 3 methods. Yeah. 1, 2, 3, here we already have 2, but I give the third one easy, mathematical function. Yeah. Mathematical function. We use mathematical function directly, in the library. Yeah. So ask you compare the performance of the 3 different methods. Yeah. All right, so we complete this topic, and we complete part 2. Now, any question at this point? Yeah. All right. Okay. All right, so let me stop this one, and we go to the new topic today. All right, so key. Yeah. All right, so let me start part C. Today's new topic. All right. New topic. I hope I'm still in recording. Can anyone see? Oh, yeah, I saw that recording. Otherwise, I may lose my video. Yeah. All right. C.1, search unordered arrays. The big topic, role of data structures in algorithms. Data structures, yeah, another topic, but it is very important in our algorithms class. Now, so here we need to spend some time study the data structures. And in this part, I just use a very simple example to show you the role, the importance of data structure. Yeah. All right, so let's start our problem number 3. Very simple, search an unordered array. Yeah. So it's pretty easy. Unordered array, yeah, do the search, find given element. That simple. Yeah. Given an unordered array with indices from 0 through n-1, n elements. Now we want to find the key capital K. Which element has this key? Yeah. We need to find that index I such that K equals A of I. So simple, right? It's trivial. You can even say it is trivial, but here there are some basic concepts we can learn from this topic. Several fundamental basic concepts we can learn. Yeah. First, we characterize this as one fundamental algorithm problem type, search type. We have 3 fundamental or basic problem types in algorithm: search, sort, selection. 3 types. Now, here, we look at the first type, search type. Yeah. Data structure, very simple, array. We use probably the simplest data structure, array. Okay, yeah. All right, yeah. I'll give you the reference in the textbook here. Yeah. All right. So the question, why the data structures are important in algorithm design, the first question. Yeah. We know everyone knows data structure, they're very important, but why it is important, right? Why it is important. Yeah. Here, I just only want to tell you one sentence to tell you the importance. Organize the data. Through data structures, we can make our data well organized. Yeah. All right. If you do not use data structure, your data randomly arranged without any structure. No structure. So then, your algorithm cannot take advantage of the structure property. So that means your algorithms cannot go very far. You cannot apply many advanced algorithms. You can only apply relatively simple algorithms because the data is so messy. So messy. A lot of advanced methods cannot be applied. That's the reason. But if you use some special data, appropriate data structures to organize your data, after that, your data follows some special properties. Then your algorithms can take advantage of those properties. So then you can develop some really advanced, smart algorithms. That's the basic reason behind it. Okay. All right. So let's look at the solution. Solution should be very simple. Yeah. Very straightforward. All right. Okay. Yeah. All right. Analysis. The basic operation for this question, we need to apply some basic operation. Yeah. Here you can see we do not need addition, we do not need multiplication, right? But we need another commonly used basic operation, comparison. We need to do comparison. Greater, less, or equal. Right? Greater, less, or equal. That kind of comparison. Okay, all right. So now compare k and a of I. Yeah. You start I from 0. Yeah. So you just write a for loop. You can easily go through, you compare one by one in sequence from beginning to end. Right? How simple it is. If k equals a of I, returns index I. The function, the search function, your search function returns index I. If not equal, then, all right, you do iterations. You compare k and a of I plus 1. Yeah, keep doing iterations like this. Yeah. Return -1 if you reach the end, because the index of the last element equals n-1. After you hit the last element, still not equal, return -1. So when you see -1, you know the search fails. Yeah. That's a result, that's an outcome. Yeah. All right. Okay. Yeah. So that's simple. Yeah. So here our focus, not here because this is so easy. Yeah. So our focus at other parts. Yeah. So we want to use this one to learn some basic concepts. Yeah. First, this algorithm we call a sequential search or linear search. Yeah. people use these two names frequently. Yeah. Sequential search, or some people like to call linear search. Linear, okay? Yeah, follow the line, so linear search. Sequential search, yeah. All right. Here, the first question we want to answer, how do we measure its performance? Efficiency, performance, how fast? If you want to tell people how fast this algorithm is, you need to find a measure for it. Yeah. So this question we need to answer. Performance measure or efficiency measure here. Yeah. Count the number of comparisons. Yeah. Here, the basic operation is the comparison, so we just count the number of comparisons we need. Yeah. All right. Yeah, so here, let us count in this way. Right? Yeah. If k equals the first element, number comparison 1. If k equals the second element, 2 comparisons, and so on. Okay? The last one, you need n comparisons. No match, n comparisons. Now, so here you can see, if k equals the last element, you need n comparisons. But if there is no match, also n comparisons. You need to go do the comparison for all the elements. Then you can say no match. No. All right. Next, some basic concepts introduced here. First, if k equals a of 0, the first element, we call it the best case. Yeah. Because for this case, we use the smallest number of comparisons, only one. So we call the best case for this sequential search algorithm 1 comparison. All right, yeah. Then the last 2 cases, the worst case, n comparisons. Yeah. 2 concepts, best case and the worst case concept. Okay? For different situations, we need to use different type efficiency measure. Yeah, efficiency measure here. Yeah. Best case and the worst case. All right. Now the next, the most important question for this part. How to measure the overall efficiency. Overall efficiency. Yeah. Best case. Can you use best case as overall? No, we cannot. Because that's a single one. All the other cases do worse than that. Can you use the worst case to measure overall efficiency? Still not. Too pessimist, right? Yeah, best case too optimistic, right? Too optimistic. Yeah, not as good as that, right? So you need to find some fair way to measure overall performance, efficiency. Yeah, not the best case, not the worst case. Measure should include all the cases. You need to factor in all the cases in a fair way, right? Fair way. Yeah. Okay. Yeah. So here, we need to make some assumption here. Yeah. It's a little more complicated. We need to make some assumption here. Yeah. Assumption is, yeah. Each case, do we have any information about how frequently these cases happen? We don't have that information, how frequent they happen. So that information we need to put into assumption. Assume these cases have the same probability. Yeah. In general, yeah, we assume that. Yeah. 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 But the probability for yeah, index case, yeah. Your function return an index. Your function return -1. Yeah, yeah. So here, match case. There is a match, no match case, right? These two cases, we need to assume some probability here. We need to use little p to represent there is a match. All right, yeah, probability. Then its complement, -1 case, complement of that, 1 minus p, the probability. Yeah. That's our assumption. With this assumption, then we can write overall efficiency. We can write the formula for the overall. Yeah. Otherwise, if you do not have this information, how can you write it? Okay? How can you use a fair way to write it? All right, yeah. So next, we can write it. Yeah. Oh, yeah. Next topic, average efficiency. We write a formula for the average efficiency. Yeah. Yeah. Basically, we take average, but this average slightly different. You know how to take average. Yeah. You know how to take average of two numbers. But here, we have many numbers. We need to take average, but there is a probability to be considered in your average. Yeah. So this kind of average we call the weighted average. There is a weight. Yeah. Weighted average. Yeah. Here. So let's do the weighted average. Okay. All right. How do we do the weighted average? We put a weight. So each subcase, there is a weight. We associate appropriate weight number. Yeah. Two-step calculation. Subcase averages and overall average. Yeah, there is a subcase. Yeah, the subcase average, then overall average. Yeah. So we do in that way. Yeah. All right. First, let us consider all these n cases together as the subcase. Yeah. One subcase covering all these n cases. Yeah. Each one probability 1 over n, right? Yeah. That's our assumption. Yeah. So now, how many comparisons for this subcase? Look at the subcase. Okay? Yeah. Weighted, this is also weighted average, but the weight 1/n, 1 over n. Yeah. Or another way you view it, you just add up all the comparison numbers divided by n. Yeah. That's our usual understanding of average. Adding up all the numbers divided by number of items. Yeah. So that is our subcase average. Yeah, because this number is covering the subcase. Match case, match subcase. Yeah, there is a match. The first subcase, there is a match. Second subcase, no match subcase. Yeah. But, sorry, yeah, I need to go forward. Yeah, no match subcase, only one case, so average is itself, yeah, only one number. Yeah, yeah, all right. But for the first subcase, probability is p. The second subcase, the probability is 1 minus p. 1 minus p. Yep. Now that's the weight. First subcase, the weight is p. Second subcase, the weight is 1 minus p. Weighted average. Okay? So let us write the formula. Combine two subcase averages based on their probabilities as the weights. Yeah. The number of comparisons for the first subcase, multiply its probability as the weight. The number of comparisons for the second subcase, multiply its probability as its weight. So this number is the weighted average. So at the end, we write this formula. Right? Yeah, that's it. So, but you need to understand the meaning. When you apply it, you need to understand what's the meaning. Yeah, the P and the whole story. Yeah. And when you, because usually when I give you questions, I describe some environment. Okay, give you some conditions. So then you need to, based on your understanding, do some appropriate modification. Then you apply the formula in the right way. The reason I say this, because many times, based on my experience, many students, they just find the formula and plug in. They may not do necessary modification, because sometimes I may put some special condition to change something. I put some condition to change something. Okay? So then you should be very careful when you apply the formula. All right. Any question at this point? All right. So we complete. All right. Next, after we have the formula, now I want to introduce another important concept called dominant term. Dominant term. So here we do some preparation of Module 2. In Module 2, we will learn asymptotic notations. So in order to understand asymptotic notations well, we need to learn this concept, dominant term. Here you can see we have many terms. Some term dominates other terms. That's important. So here you can see this +1 is not important because it's small. Okay? If we look at the number, especially when the number is big, this +1 is very little. We can ignore it. If we look at the dominant term, we can ignore it. So you can see, to look at a dominant term, those minor little terms can be ignored. So n is the variable. If we combine all the coefficients of n, here let me write something a little. From the first part, 1/2 n plus 1 ignored, so you have 1/2 p times n. The second one, all right, 1 minus p, all right, be careful. Do not ignore 1 here and minus p, do not ignore that, because n multiply this number. You cannot ignore. Here, n plus, plus this number, we can ignore. Multiply, because n is big. Think about it, n is big. If we ignore some number inside the parentheses, after multiplication, it could be very big, right? So don't ignore. Sometimes one cannot be ignored. Sometimes this one can be ignored. Depends on the position. All right? So the second one, the coefficient is 1 minus p times n. Now you add 1/2 p plus 1 minus p, you get this 1 minus 1/2 p. That's the coefficient of n. N is the variable. P is constant. Given constant. 1 minus 1/2 p, that's the coefficient of n. So this whole thing together, we call the dominant term of this expression. Average case efficiency expression. Dominant term. The remaining minor terms, remaining minor terms. Now sometimes we can ignore the minor terms. Yeah. All right. So that's the topic C.2. Yeah. Next, we have this new topic we call the repeated squaring technique for polynomial evaluation. Here, this one is a smart method to calculate some special expression efficiently. So here, let me explain this method. Repeated squaring technique. From its name, you can see how do we, the content of this method. Yeah. All right. Let me show you, a simple polynomial. Yeah. All right. So this is a simple polynomial. Yeah. All right. And when we do the evaluation, so here let me just change the color of my pen. All right. Okay. So when we do the evaluation, we just learned Horner's rule, right? Yeah, Horner's rule. Here we know the Horner's rule is used for the general case. Yeah. So why it's the general case? Because here A0, A1, AN could be any numbers, right? Yeah. Very general. We do not require A0, A1 through N follow any special pattern. We do not require any pattern. You can apply Horner's rule. Okay? Yeah. All right. But when you have special case, when we have special case, so for the special case, Horner's rule may not be the fastest. Because on the special case, we can do faster than Horner's rule. Here we consider the special case. Okay, all right. Here we consider, look at this. Yeah. Suppose I use P0 of x, this polynomial, equals x to the nth power. Is this special? Special, right? Yeah. Yeah. Monomial, only one term. One term, no coefficient, or coefficient is 1. Okay? Yeah. So it's a special case. That means you can use the special property in this case to get a better performance, better efficiency. Yeah. Think about if, for this special case, if you apply the Horner's rule, it's not very good, it's not the fastest way. If you apply Horner's rule, because Horner's rule tells us the number of multiplications equals the degree number m. Here, if you use n multiplications, not very fast. Not the fastest way. Not the fastest way. You can do better than that. You can do faster than that. Yeah. Here, so look at a special example. Yeah. Look at x to the 8th power. How about that? 8th power. Yeah. This 8, we know it is a power of 2, right? 2 cubed. 2 cubed. How about that? The number is special. We have special property. Why we do not take advantage of the special property? Right? We can take advantage of it. Oh, question.
Is this like where you can reduce the number of multiplications since like 8 is a multiple of 2, you can like do, instead of like repeated multiplications, you can do multiple square roots, or like, so you can split up into
Right.
x squared, squared.
Yeah. Yes, you got a point. Yeah, you got. So go back, look at the title, repeated squaring, right? That's what we are going to do. Yeah, because power of 2, we can take advantage of it. Power of 2, right? Yeah, because look at the smart way to do it. Smart way. All right, yeah. Let's do it. Yeah. First, from x to x squared, one multiplication, right? Yep. X times x, one multiplication. All right. Next time, when you move to the next one, you can go faster. All right. How about, because you already have the x squared value, how about you multiply x squared by itself, just the one multiplication, you can go to x to the 4th. How about that? Another multiplication. Another multiplication, you can go from x squared to x 4th. You only add 1. You jump faster. X to the 4th. X to the 8th. This time, you already have x to the 4th. How about you just take another multiplication with x with itself, squaring. Here, that's the squaring. We keep doing squaring operation. We jump to x to the 8th. Another one multiplication, you can see, adding these 3 multiplications together, we only need 3 multiplications. We can find x to the 8th. Instead of Horner's rule, we need 8. From Horner's rule 8, we reduce it to 3. How fast it is. Think about that. Repeated squaring, how fast it is. Repeat squaring. Okay? All right. Let me ask you another similar question. X to the 1024. If we want to calculate this monomial, tell me the minimum number of multiplications we need. Minimum number of multiplications you need by repeated squaring. It's a power of 2. I think you know it. 10, great, yeah. So here we want to compare the difference. All right. By Horner's rule, for this high degree polynomial, you need 1024. By repeated squaring, we only need 10. Look at the reduction, how big it is. Look at the reduction, how big it is. 1000 to 10. 1024 to 10. Is that huge? That's huge. Yeah, that's huge. Okay? Yeah. So Horner's rule, we know it's smart, but not necessarily always smart, right? For general case, yeah, because general case, we don't have the pattern for the coefficients. So we cannot take advantage of any special properties. But for the special cases like that, we have the patterns, right? We can take advantage of it. How about that? Okay? All right, yeah. Next, let me give you another example. So here you can see, for this class, you really need to open your mind for your thinking. Try very hard to explore all the possible ways to solve the problem. So here, let me give you another interesting example, and to see if you can solve it or not. This time, I give you this polynomial. All right. My question, because here I give you special numbers. There is some special pattern you can take advantage of it. Definitely you can apply Horner's rule. If you apply Horner's rule, you will get 4 multiplications. Based on our previous experience, can we take advantage of the pattern of the coefficients so we can apply some special property, take advantage of the special property, and do it faster? How about that? Do it faster. Yeah. Think about it. Yeah. Horner's rule. Yeah. Yeah. We assume Horner's rule, right? Answer is 4. Okay? The Horner's rule, the answer is 4. So that's our bottom line. Yeah. That's the worst we can do. We want to do faster than that. Yeah. That's the worst we can do. Okay? Yeah? So you should get numbers smaller than 4. Then it's accepted. Yeah. Worth the effort. Yeah. Otherwise, we just take the Horner's rule. Think about that. Anything special in this polynomial? Anything special? Any pattern you can explore. Yeah. Here, let me give you an important keyword. If you have that experience, you will get there quickly. Pascal triangle. Anyone knows Pascal triangle? Pascal triangle. That's the keyword. Okay. All right. Triangle. That famous triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. This 1, 4, 6, 4, 1. Related to our coefficients. Pascal triangle, these coefficients, what's the relationship? How do we take advantage of it? Take advantage of it. Special coefficients. You should take advantage of it. What's the meaning of that? Do you know the meaning of Pascal triangle? So here the knowledge, if you have the background, that knowledge, although you can do web search, but you need to study a little bit. Okay? Yeah. So here, let me tell you the meaning. Yeah. That one, the top one, corresponds to a plus b 0th power. The second line, the coefficients correspond to a plus b to first power. The third line, a plus b square. Okay? Then next line, a plus b cubed. Then this line corresponds to a plus b to the 4th. If you do the expansion, a plus b to the fourth, do expansion, multiply out, you get this, the coefficients 1, 4, 6, 4, 1, based on Pascal triangle. All right. So from there, yeah, does it help? From there, a plus b, x plus 1 to the fourth. How about that? Our p of x equals x plus 1 to the fourth. X plus 1 to the fourth. How special it is? X plus 1 to the fourth. How special it is? 4 power of 2, right? Square. Repeated squaring. Can you do repeated squaring? Repeated squaring. Do repeated squaring. All right? Repeated squaring. First multiplication. Because we do not count addition. X plus 1, we do not count. Okay? Think about that. We do not count addition. Because it's so cheap. We don't count it. Okay? All right. X plus 1 times x plus 1. This is the first multiplication. Okay? The second, x plus 1, yeah, here. So the second, x plus 1 square times x plus 1 square itself equals x plus 1 to the fourth. So that's the second multiplication. How about that? Total 2. You see, this polynomial, you need 2 multiplications by repeated squaring. Yeah. By repeated squaring, for first view, it may not be that obvious. How can you apply repeat squaring here? Because you identify it as x plus 1 to the fourth by Pascal triangle. Pascal triangle. So you identify it. You find the relationship. You just take advantage of it. Take advantage of it. You get answer. From 4 to 2. That's the answer. Try to use this simple example to get what we are doing in this class. That's the so-called smart way to solve the problem. Okay? Yeah. I do not give you very complicated questions. This simple question, right? But you can see, based by the knowledge we just learned, we can already do things like this. How good it is. How powerful is the knowledge? Think about how powerful is the knowledge. Without knowledge, you cannot do things like this. So that's the knowledge we want to learn in this class. Yeah. So many things like this. All right? Yeah. Okay, the break time. Yeah. So come back